This is about a new brushless machine. So you explain why we need this type of a brushless machine for practical application. Then you introduce yourself, introduce the project details, and tell that this is the TRT type of machine where one of our seniors had developed the brushless DC motor, which is of 5 kilowatt. So which we will be fabricating and use and intend to use in future. Okay, so during this time your video will run. So in Katrina, you try to explain about the grand challenge, the background, why we need to have this type of grand challenge for future solution. Then we choose urban infrastructure because we want to make the city to become carbon free. Then you talk about how is today it looks like, high carbon density, low sustainability. So in our perspective, smart city include a smart communication grid and smart transport. So smart transport is a part of the urban infrastructure, which is why we choose this grand challenge theme as urban infrastructure. So using this solution provision, so what we expect is then low carbon density and high sustainability in the future. Then on-road capability, you can explain about carbon emission. These are the few models available in the market. If you want, you can explain individually the car model. Otherwise, just tell this is these are the different type of EV, HV available in the market. Then this is about the performance also. You can explain individually, like Estima moving up or Estima moving from 3.5 2.4 liter, but still the efficiency and the low emission. As the time moves on, you can see the comfort level is also increasing. At the same time, the efficiency also increasing to the greater extent. So the Paris 3 is 3 times reduced the volume of Prius, but 2 times better than the performance of the initial model. Okay, so this is a simple representation for understanding the power density. So as we can see here, the road available Lexus is 4 times better than the performance of the Prius within the span of 4 years of time. So this is the way in which the traction motor technology or the HEV technology is moving forward. Then you explain about this graph. Then you say that in electric vehicle we are much focused on the forward motoring, which is important in terms of riding on the road, also the slope. And reverse braking or regenerative braking, it is used in the sloping down or this one. Then you explain this curve. This is a constant torque, constant power, reduced power region. So our purpose is basically, if you want to have a extended operation during the sloping condition, either going up or going down, you need to have the power region to be bigger, so it cannot drop straight away, it cannot drop abruptly. So extended power range is important during sloping condition, the supplement for the torque requirements. Then you explain about this traction motor characteristics. You explain about hybrid, full hybrid, mild hybrid system. Then you explain the different stages of this car function. Okay, then you explain about how this power flow happens in this case of motor generator operation using either this picture or this picture. Then you say that what happens during acceleration is rotating one direction, braking it is going out in the other direction. So then you explain this is a Kamalini, this is one of our senior model, Kamalini model. This has an outer rotor machine, which is a 500 watts 45 volt VLDC 2300 RPM machine. It takes a current about 10 amperes. Then you show your practical model. You explain to them practical model how it looks like, Then you see that the drawback of this model is the mechanical gear is introduce a lot of losses, because essentially after we do this one, we need to have a gear system. That means mechanically you have to connect this one to the another mechanical drive. So in this approach, what we want to do is we want to have a magnetic gear attached to this mechanical system, whereas when this is revoluting at one point of time, your gear can rotate simultaneously depending upon the output characteristics. Say for example, if you have a magnet here, so I put another magnet here. If this magnet is rotated because of the electric vehicle, your external will be connected to the actual wheel. So when this rotate one direction, your external will be rotating 3 times if you are using 1:3, so that your rotation will be faster or the gear will be more. So he explained something about here on those aspects. Then we see that how we know that this is the characteristics required for the electrical motor. This is a conventional system. We can talk about first gear, second gear, third gear, fourth gear. Then if you trace back on the surface, you will get some characteristics like this. So your electrical motor should have a characteristics like this. If we are able to get a characteristics like this, that means your electrical motor will be better in performance. A brushless DC motor essentially will produce characteristics like this. As you can see, it's a constant DC. Then you want the voltage to drop to here, then drop to here. So this part is what constant torque, this part is what power density, power part, this is part your reduced torque. Then you explain about this one comparison to IC engine. This is IC engine, this is internal. IC engine, you can see here it takes some time to respond, whereas electrical motor starts straight away from the high condition. So that means there are a lot of energy loss in this case. In this case, it's no energy loss. That's why electrical motors are preferred. Most of the carbon emission is coming during the starting period and during this resting period. So we can avoid that one easily by having an electrical motor as a replacement. Okay, so in order to have the variation of the gears, high gear and low gear, so we propose here as a magnetic gear brushless DC motor. So this can be done using the control of power electronic system. Okay, then you leave this one to Wei. Wei will start explaining about this one, then explaining about the concept of this one. He said this is the Kamalani model, inside out. Kamalani model, inside out. Then you ask about this one, then he said this is the magnetic orientation. You can tell that there is an air gap or there is a magnetic sleeve in between these two magnet surface. Because if we don't tell that one, then there is no magnetical jumping. So you have to tell there is a magnetic shield or a seal is there in between the magnet. Then you explain about this flowchart, this block diagram, but don't need to spend much time. You just tell this part, then you just tell this part, then how we do the solve. Don't need to spend much time on this one. Then you say that for the same volume of what done by our seniors, we design the same machine with a 1:1 ratio. Then we try with 1:2, 1:3. Then this one shows the magnetic flux flow for 1:3. I can see here, as you can see that magnetic flux is divided into 3 here, but at the same time the concentration of the flux, if you see, it is more here is more dispersed, here is more converged. So more converged means more flux density. Okay, this is the magnetic flux characteristics of the machine. As if we can see from this graph, there is an improvement, considerable improvement in the torque. So if you want, you can tell the percentage improvement of the torque in this case. Then the trapezoidal characteristics, it is suiting to the BLDC drive. If people ask, then you tell the difference between PMSM and the BLDC machine. So if we have a trapezoidal characteristics like this, then if you need to use a power electronic that can produce exactly the same characteristics, then your harmonic will be less, then your drive is very efficient. For example, if the same thing, if it is producing a sine waveform, then you have to use a sine drive. In that case, it is called as a PMSM type of machine. Of course, you need to have a Hall sensor to sense the position, because we need to know when the power electronics need to produce high, low, negative, high, low, like that. So I need to know the position at each value. So usually what they put is, they will put Hall sensor at the circumference of the rotor, so that the Hall sensor will give a feedback to the power electronics, and the power electronics will decide where to do the pulse width modulation, so that it produces a pulse which is same as that of your output flux linkage at the back EMF. Then you explain about the gear operational condition by putting the value in terms of the coil excitations. Then the traction findings, as you can see here, this is extended power is already achieved here. So you can say that there is an improvement in the from the conventional design, which is about 30%. And in terms of the volume to magnet torque to magnet volume, there is an improvement in 25.21%. Because essentially they will ask, now you are increasing the magnet, so is it not the volume is the same? So you have to justify. Definitely that question they will ask. Okay. Then the motion analysis, in order to find whether it is ready for the road condition, we use a software tool wherein we try to plot a different point of the time condition for one cycle of a vehicle operation, and we find this is exactly following of what we wanted in this given condition. So you can see that the acceleration is dominated by perfect slope, and the deceleration is also by the perfect slope here. So when we compare the conventional that of the proposed one, you can see there is an improvement in the performance in terms of sloping. That means, for example, the conventional one can slope at 80% only. The proposed one can go up to 140% at the slope. So what we can conclude from here is the proposed machine can have a better performance in terms when it is particularly when it is moving up and down of the system here. Then we developed the prototype in the lab using a 3D printing. This is just to show the actual figure. You can see this is the magnet, outer magnet, inner magnet. There is a magnetic sleeve between this one, and this is the stator conductor where we can give the current or take the current from here to charge and discharge of the voltage current. So project innovation points from this include improved performance comparison that of EHV market, so it's sustainable. So we can use a trapezoidal machine, so it is apt for BLDC. Then it is a 3 different type of magnetic design can possible, but if your sizing is bigger, we can have a better some more ratio also possible. Okay, so 29.3% improvement in motor constant square density. This will identify the ratio of torque to the volume. So torque improvement is about 33%, and there is an 8.9% improvement in the torque density. So the project summary to conclude: challenge of traction drive is how to respond through different operating zone. So mechanical gear is a drawback. So we propose a magnetic gear with extended operating capability in sloping condition. 3 different ratios used with and that can 3 different ratios, and all produces a trapezoidal characteristic which is more suiting for BLDC type of operation. This will also help the reduction in the torque volume will increase the dynamics of the system. One by extending the power operating zone, and second by increasing the power density of the system. Thank you very much.